What I'd like to do now is demonstrate some of the main features that are associated with anisotropy through an example that is relatively simple, but it will help us highlight major features that I have previously indicated in the discussion of anisotropy, and it will specifically help us demonstrate what normal shear coupling means and how that is induced depending on the orientation of anisotropy. All right, well, we've made several remarks earlier when we were discussing the topic. We're going to consider an example that is sufficiently complex to require a numerical solution scheme, and this is a program that's able to do that based on the method of finite elements. All right, so we have a very simple geometry, but still it does not allow us to calculate the solution in closed analytical form. So we're using this program, and we have a plate with a hole. And this plate has free surfaces on all sides, okay? So everything is free except for two surfaces, okay? So free means, remember, I'm not applying any force. If the plate wants to deform in some way that it wishes to, then it is free to do so. First of all, notice the coordinate directions. We have x, y, z. So x equals 0 is the back surface of the plate here. X equals 1 is the front surface. Y is along that direction, and z is along the axis of the cylindrical hole cut, if you like. All right, so now all the surfaces are free except for x equals 0. At x equals 0, what we're saying is that none of the points which lie on that surface can move anywhere. So they are rigidly fixed there. It's as if I take this plate, adhere it to that surface, or bolt it, whatever. The plate cannot move anywhere on that surface at x equals 0. The other surfaces are again free except for x equals 1 surface. Is this front surface over here, and at that front surface I will impose only one condition, namely I'm going to let the plate move and deform in any way it wishes to along the y, that's the vertical direction, and the z directions. So I'm not going to apply any force along those directions. If it wants to, it will be able to deform, but along the x direction I'm going to constrain it to move by the same amount, only along x. So it's as if this is metal, and I put in an earlier example that we use, for instance, in the case of thermoelasticity, it's as if I put a strong magnet here, and that magnet allows the plate slide freely on it, but when I pull on the magnet, it makes the plate move with it. And because the magnet is rigid, all the points are going to get displaced by the same amount along the x direction. So that's the constraint. It's free on all surfaces except, including the inner surface of the cylindrical cut, it's free except for at x equals 0 where the plate is fixed, and at x equals 1, only along the x direction I tell it how much it should move. Along the y and z directions, the plate can move in any way it wishes to. So that's the structural problem. But to solve the problem, I need some material information, and that information is going to be assigned through this tab here. So notice that all the analysis that we're going to do is going to be based on linear elasticity. Eventually, the deformations you'll see are a bit exaggerated, but the analysis is going to help us demonstrate major qualitative features that we are seeking. So the exaggerating deformations are just so that we clearly see what is happening. Okay, if you like, they are magnified. So the first type of material behavior I'm going to impose is isotropy. So it's isotropic, and therefore I know I need to apply only two constants, the Young's modulus and the Poisson ratio. And through those, I can determine the material properties, in particular the compliance matrix. Okay, so the program knows exactly what the compliance matrix looks like because I know E and the Poisson ratio, and those are the only two parameters I need to determine the compliance matrix. The shear modulus is a function of those. Now notice that first, the Young's modulus is chosen to be 1. The units, don't worry about the units. This is Pascal's, it says, but it could have been gigapascals, or this could have been 100 gigapascals, could be more realistic if this were, say, metallic, but ultimately the value of the Young's modulus is going to only scale for a given deformation, the stresses I measure. So if you like, for numerical purposes, I'm scaling down the stresses, and the units of stress here is assumed to be of the order of the Young's modulus. Okay, so whatever the units are. So here I picked it to be 1 something. Don't worry about the Pascal. Okay, so, but the Poisson ratio is important. What I pick it to be will be important, but I picked it to be 0. Remember that I'm allowed to pick it to be 0. It can be anything between 1 and between 1/2 and -1. I picked it to be 0 so that eventually when I move to the next stages, I shall be able to compare the material behavior in a more realistic fashion. There, choosing a 0 Poisson ratio will be a little bit more helpful. All right, so those are the material parameters I need to supply. That's all. The problem is well defined, so I can go ahead and solve for the problem, and eventually I go ahead and I compute. We wait for a while, and that is the result. And so that is the deformation. And here what I'm plotting is, first of all, visually you see that initially the plate was square, and now after I pull along the extraction on that surface, the plate has only moved along the extraction. This surface is free to move along the y or z directions, but it doesn't. It only moves along the direction I prescribe. And simultaneously the color blue indicates, bluish colors indicate that a point has moved down. I can visually see it. The point, eventually these points move down. And when I see yellowish, reddish points, orange, they indicate that the point has moved up. So I see that both visually and also through the colors. So if I do the small visualization of the deformation looks like this, right? So the point that was here, it moved down. The point that was here, it moved up. And that's the way the deformation looks. Now, notice that the Poisson ratio is equal to 0. So therefore, you don't really expect significant contraction here. But here, you seem to have contraction. Those contractions are not due to the fact that the Poisson ratio is positive. Indeed, it's not. It's due to the fact that there is a hole here which reduces the stiffness of this cross-section, and therefore you seem to have contraction. But that's a structural effect. The material behavior has no contraction, which is sort of observed here. The material does not contract. It's free to do so, but it doesn't because Poisson ratio, or it does so very little if we don't see it, because the Poisson ratio is 0. So that's the case of isotropy. So probably no surprise. This is more or less what I would expect to see. Remember the shape for reference of the hole after it deforms. So if you like, when I refer to it, you can go back to the video to this instant and have a look at the shape of the hole after it deforms. So now I want to pick a different type of material behavior. Again, I go back to this linear elasticity choice. Now what I like to do is I'd like to use the carbon fiber plate example that we solved in the videos earlier, and in which case there were carbon fibers running along the x direction, okay, and that was all, no fibers along the y direction. So we have epoxy carbon fiber matrix, epoxy matrix carbon fiber composite, and along the x direction in the example we solved, the Young's modulus was larger, of course, due to the presence of the fibers than along the y direction. So now we have 3 directions and the program requires 3 values. So first of all, the fact that I'm choosing a n-isotropic material requires that I indicate that in the program. So it's not isotropic. First, I'm going to go pick the choice of orthotropy. Now, when I do that, just like in the example, I need to supply, in the analytical example we solved, I need to supply the values of the Young's moduli and the shear moduli and the Poisson ratios. The values are borrowed from that example we solved. Along the direction of the fiber, we had 76. Forget about the units, if you like, 76 GPa. We're omitting the giga part. And here, along the y direction, along the direction perpendicular to the fibers, it's 5.5, just like in that example we solved. And I need to supply the third direction, which is also perpendicular to the direction of the fibers, which is also 5.5. Now, the shear moduli, the shear modulus in that example we saw was 2.1. I assigned it to be, just for simplicity, to be 2.1 for all directions. So this may not be very realistic. I just borrowed the values. And again, in that example we solved, the Poisson ratios were not zero. There was a Poisson ratio xy and yx. They're not the same. I just assigned everything to be zero. Again, this is not necessarily realistic from a composite mechanics point of view, composite materials point of view, but I've just assigned it to be zero so that we can think of the structure of the compliance matrix more easily. So remember, the compliance matrix for the case of orthotropy requires 9 quantities, 9 inputs, 3 Young's moduli, 3 Poisson ratios, and 3 shear moduli. So I've supplied those 9 independent parameters here to describe orthotropy. And moreover, because the Poisson ratio is 0, and because the fibers, and this is very important, because the fibers here are assumed to be running along the x direction. How do I know? Because Ex is greater than 0. How do I know that, okay, Ex is greater than 0, but does that indicate that the fibers are running along the x direction? Well, actually the program, when you choose orthotropy, and because this second item is selected, it understands that this orthotropic behavior is such that the orientation of the fibers is with respect to the standard direction. So in other words, the values that I'm entering, for instance, when I say Ex, it has to do with the fiber direction, fiber reinforcement along the x direction. So I understand 76 has to do with fiber reinforcement along x, and eventually looking at the values, I would deduce, for instance, that there is no reinforcement along the remaining direction. So this choice, that material data ordering is standard, is telling the program that the orthotropic material is oriented along the x direction for the fibers, and the other directions have no reinforcement. So that's an interpretation based on those values. So it's important I tell the orientation of the fibers. So that information is implicit in here through my choices. Good. So with those choices, the compliance matrix, if you look at the full structure of compliance, don't look at the 2D example, the general 6x6 form, it's diagonal because one, when axis of orthotropy, the direction of the fibers align with the coordinate directions, we know that there is no normal shear coupling. Okay, the material is anisotropic, nevertheless there is no normal shear coupling. Plus, because the Poisson ratios are 0, the off-diagonal components in the normal coupling submatrix, they're also 0. So there are only diagonal components of the normal coupling and only diagonal components of the shear coupling submatrices active. Everything else is 0. Okay. So then, well, what is it that would come out of this? The same study with this choice of the composite material or composite plate manufacturing. Okay, so to see that, let's go ahead and calculate the outcome. So again, we do the solution, and that takes us to the final deformed stage. And what we see is qualitatively a feature that is similar to what we've seen before for the case of isotropy. So Poisson ratio is 0, not much happens here. I just pull on the plate, the fibers are running along the x direction. So I've extended the fibers. Probably if I had plotted the stresses, they would be huge because, well, compared to the previous example, because now there is great amount of reinforcement along x, not so much along y. But what's important is that qualitatively the deformation is similar, and the plate, the points that were here, they moved. The points that were above the plate, they moved down. The points that were at the bottom of the plate, they moved up. The deformation is symmetric, very much like isotropy. How do I know that this is not actually an isotropic material response? It's hard to say, really. You have to have a very trained eye. So in this case, perhaps because of the deformation of this hole into this new strange shape, which is differing from the one that we had obtained earlier for the case of isotropy. So maybe that's an indication, but it really is not easy to tell that this material was not isotropic, right? Now, Now we're going to change the problem. And what we're going to do is we're going to go back to the setup. And we're going to say the following. Well, previously I manufactured this plate, composite plate, out of, perhaps I cut it out from a larger composite plate such that the fibers are running in this direction. Now I'll take a composite plate and cut this plate out at an angle that is skewed to it such that when I put this plate on this structural problem, the fibers do not run along the x direction, but rather at an angle that is skewed to the x direction, but still in the xy plane. So they don't have an angle with respect to z, so it's still perpendicular to the z direction, but they have rotated along the xy direction such that the angle they make with x or y is 45 degrees. Okay, so from here to there they run along the diagonal direction, everywhere else parallel to it, okay, at an angle of 45 degrees. Remember it, in that direction, from the bottom to the upper right hand corner, right? Okay, so here there's a cut, so I cut out that portion, but there are still fibers everywhere. All right, so now the orientation has changed. Now that the orientation has changed, in particular what it turns out happens is that you get normal shear coupling. We're going to see that in a second when we calculate the solution. But because that happens, the form of the compliance matrix now is not going to fit in the standard form of orthotropy. For the standard form, there is no normal shear coupling. So for the standard form, I only supply 9 values, and you, with the knowledge that you have, there is no way you can figure out that those off-diagonal normal shear normal coupling parts if the orientation is not at a direction that aligns with the coordinate directions, with the directions of loading. Okay, so now therefore it turns out the material still has 9 independent components. It always does. That's the case of orthotropy. But because the orientation of the fibers are different, you have to recalculate the compliance matrix. Now the calculation, the exact calculation, depends on or is going to be covered, could be covered, let's say, in an elective course on composite materials. So we're not going to do that. It's not really that hard, but I'm going to go ahead and enter the resulting compliance matrix as if I had some general anisotropic material. So I'll pick the choice of anisotropy, and as soon as I do that, I will have to enter the compliance matrix in its full glory, in 6x6 form. Here what I'm entering is not compliance but the inverse of that, the stiffness, okay, just for the reason that this is what the program requires. Okay, so but in any case the compliance and stiffness, they show similar features. In particular, you see here there is a 3x3 portion which has to do with normal coupling. When I say coupling, normal, it couples normal strains to normal stresses, because this is stiffness, not compliance. Okay, so on the right we have strain as a vector 6x1 multiplied by the stiffness matrix, spits out as a result 6x1 stress as a vector. Okay, so this is normal coupling, this is normal shear coupling, this is shear normal coupling. Again, you observe the symmetry that we're supposed to have. Okay, so this is 4-1, this is 1-4, this is 4-1, this is 2-4, this is 4-2 component, they're the same. Okay, symmetry is still there, and this is shear coupling. All right, and notice that the values are slightly different now. They are not the same, unlike the orthotropic case, because of the rotation. And likewise here I've got off diagonal terms within the normal part. So again, that has to do with rotation. More importantly, the terms that have to do with normal shear and shear normal coupling, they're not zero anymore, which means there will be some coupling. Okay, so now let's see how that coupling comes into play. Remember, all I've done is, instead of making the fibers run in that direction, it's exactly the same material, but I've made the fibers run along the diagonal direction. Okay, so let's go ahead and first calculate the solution, or compute it, more correctly stated. And that's the solution. Okay, so we're going to go ahead and plot it, but before we visualize or animate it, we see already that all the colors are almost blue except for this portion, which means that everything is moving down, and I see that visually, of course, but the colors just highlight it even further. So remember, I just only applied a displacement along the x direction, and the plate is free to move along the y and z directions. In this case, the orientation of the fibers is at an angle that's skewed to the coordinate at x-axis, so but still perpendicular to z. You don't get any motion along the z direction. Still, motion along z is 0, but now there is motion along the y direction, and in particular, it moves down, all right? So, and it's free to do so, so it does, but it didn't do it for the case of isotropy or for the case of orthotropy with a fiber orientation parallel to x. It did so because the fibers are now running at an angle of 45 degrees, okay? And what's really happening is, as I pull, you may want to think about it yourself. One interpretation is what's happening is the fibers are at an angle of 45, and it's very hard to deform that. So to the extent possible, they are trying to preserve their lengths, and the way they preserve their lengths, if you pull in that direction, is if one tip of the fiber is attached to the other point if the other tip moves down. So remember, or imagine, if there was a point here that the fiber is running from here, that corner, to that corner. To preserve its length, this tip needs to move on a circle. As it moves on a circle, the tip of the fiber, this end is fixed, this end is free, and if it moves on a circle, then it preserves its length, and so it has to move down, right? So, of course, the length does change, but it's just trying to stiffen that direction so that the length doesn't want to change that much. So it forces the plate to move down. So I just impose a normal deformation, but it also moves as if I have sheared the plate, but I haven't. I haven't applied any force along the y direction, minus y direction. So if this were an isotropic material, you would have immediately said you pulled and you pushed down. But presently, I'm only pulling, not pushing. Still, it moves down due to normal shear coupling. So that's what normal shear coupling means. So now you can imagine that if the fibers were running not like this, but in the other direction of 45 degrees across the other diagonal, when I pull, it would have moved up. Or conversely, for this example where they run in that direction, instead of pulling, if I pushed, again, it would have moved up, right? So the orientation is very important. And that's why we said that the orientation of orthotropy of the fibers is very important. And the way to characterize all of that effect is through the consideration of anisotropy, and we can easily do so. For instance, even in this scenario, I know there are 9 independent constants, but I go ahead and calculate the compliance or stiffness matrix in this case in its full glory, and I'm able to extract the correct solution from the problem. Okay, so that is the advantage of being able to work in a full anisotropic scenario, and that is what normal shear coupling physically corresponds to.